Welcome to the second lecture of the second chapter of the course. Today is the first lecture on how to do speciation calculation. Today we're going to use algebra. The next lecture would be using graphs, and then the following lecture would be using some programming and some software. But the theme of the following two lectures and also this lecture would be the same. We're going to do quantitative description of speciation. So basically we're solving for the concentration of each species in the system. And also we're going to evaluate different assumptions to do a little bit of simplification for this lecture. And also look at the impact of adding strong and weak acid to water and see how that changes the speciation in water. So today what we're going to learn stays with us for the whole course. So this lecture is very important. So we're just basically talking about the foundation of how to approach speciation and then how to solve it. So the logic would be still always the same. In chapter 3 and 4, it just gets more involved. In chapter 3, we bring metal, and in chapter 4, we bring redox reactions. So in the previous lecture, we talked about acid-base. We described the fundamentals, and we mentioned that the most important reaction is basically within the context of acid-base is water hydrolysis to produce proton and hydroxide. So this was the core reaction that happens always in all the aqueous system that we're dealing with. And we also described this special designation of Kw to relate the activity of proton and then the hydroxide. And we mentioned that this is basically 10 to the minus 14 at 25. And this changes because the K value is a temperature dependent. And then we describe the standard version of writing a acid reaction. That was basically deprotonation. So HA producing the deprotonated form, A minus, plus releasing one proton. So that was the standard approach to write a acid-base reaction. And then the K value for this reaction, we designated the special Ka for the standard reaction. As always, the activity of the product over the reactant. And we were most of the time using pKa, easier to work with. And then the last thing we talked about in the previous lecture was talking about the acid strength. And then we had this threshold of pKa less than 2. This would be a strong acid. And pKa of bigger than 2, this would be a weak acid. And a strong acid means we have more protons introduced to the system compared to a weak acid for the same initial concentration of the acid itself. So as I mentioned in this lecture and the following two lectures, we're going to talk about speciation and doing the calculation for speciation. So a very useful information. So a little bit deeper on the speciation. Basically, when we talk about a speciation, it's talking about calculating the activity of all the species. But for the sake of simplicity, we assume it's ideal solution. So we're always talking about the concentration calculation of all the individual species. And then we calculate that assuming that we're adding a certain amount of bulk concentration to the system. So we're going to talk about that through several examples here, but just a little bit a formal description of speciation. We're going to calculate the concentration of all the individual species in the system. So if we add different salts to the system, that eventually we're getting A and B and C. We want to eventually know what's the concentration and or activity of the species. So these are the species in the system. And to do that, we need to know how these species are related. So basically, we also need to know how these are related. So the relationship. So why speciation is important, understanding the speciation is important. It's because it gives us a lot of useful information about the system. For example, we would understand if we add a known amount of substance to water, what would be the solution pH? And also the activity or concentration of all the other species. Or the other way to look at it is basically if we want to raise the pH of a solution from, let's say, 4 to 10, how much of this specific substance we need to add to the system. So how much of a weak acid or strong acid we need to add to the system to increase the pH by some units. So that kind of information we're expecting to understand based on these 3 lectures. So we could have different approaches for solving the speciation. It could be using algebra, it could be using some computer software. We could do some assumptions, and also we could use graphs. So we're going to cover them all. And the best approach is always depends on the situation and the degree of precision we need. So that's another factor that we're going to consider when it comes to how to solve it. So this lecture, we're going to focus on algebra, how to design the framework of equations, and then how to approach them in terms of solving them. But the tool would be basically algebra. So if we have n species in the system, obviously to understand all the activities or concentration, we need n equations. Pretty obvious from general mathematics. So now we want to drive how to construct this n equations for that n species. So that would be our job for this lecture. But before we start constructing those equations, down the road, we might have an equation that has more than one answer, like a quadratic equation might have 2 answers, but sometimes we have to bring also our physical intuition to the table. For example, if we eventually get to the concentration of species A to the power of 2 would be 4, we know that mathematically this has 2 answers. So A could be either +2 or it could be -2. But obviously in this context, -2 doesn't make sense because we don't have any concentration of a negative value. So it's basically just the +2 makes sense. So something that we need to consider down the road. So n equation for n species. So that would be basically what we need. And to do that, we need to combine all the information we've learned so far in chapter 1 and also in the first lecture of the second chapter. So this part would be probably the most important part of this course. So very simple, but a logical pathway to solve for speciation. So for any system that you're given, it doesn't matter whether this is acid-base or like any metal involved or redox, the first step is basically to identify all the species. So it's called n species. So we need to identify all species. So we might say, oh, we have A, B, and so on. So this would be the first part of calculating for speciation. Then when we know we have n species, we need to look for n equation, independent equations. So the next step would be n equation. And an equation means how these species are related together. So the relationship between species, lecture 2 of the course. So basically what we do is basically develop equations, or how species are related. And the third part, once we have an equation for n unknowns, which would be species, the third step would be basically solving it. So step 3 is solve. We could use algebra, we could use graphs, and so on. So for the rest of this course, we're going to follow the same procedure. N species, so you have to be able to identify potential species that are there. Then how these species are related, we're going to talk about this in details. And then your tools to be able to solve for the equations. So step 1 is identifying expected species. So one thing here is that you have to be either experienced in terms of understanding what species you might expect based on what you're adding to the system. For example, when I'm adding sodium chloride, most likely I'm adding sodium chloride itself. So those sort of information, or if you're dealing with acid base, it's always a great practice to look at the tables. For example, when you add sulfuric acid, you have 2 pKa. That means you have sulfuric acid, also HSO4 minus, and also SO4 2 minus. So we're going to practice that more and more, and then you'll be more experienced. So identifying the species, expected species, is all based on the information you're giving. Either you added specific salt, or you expose your system to a specific gas, what we're going to learn also in this chapter, or you're dealing with an acid-base reaction, then you go back to the table and see what kind of acid base is that, how many pKa you have, then you can identify basically the expected species. So let's do a quick practice. Assume you're in the lab, you have a container contains water, and then you add some sodium sulfate. So what kind of species you might expect at equilibrium? So that kind of question you'll get definitely in the exam also. A very useful way to look at it. So you're in the lab, a practical situation. You have sodium sulfate on the shelf, and you add some concentration or some amount of that sodium sulfate in your system. What species you have? So you have sodium. What's that? Sulfate. What else? Exactly. So once you introduce sulfate, then that's out of your control. Then it would go through the acid-base reaction. And because sulfate is basically a byproduct acid based on the table, definitely you have the HSO4 minus and also the most protonated version. You might not have a lot of concentration of this guy because it's a strong acid, but still you have it. That's a part of your speciation matrix. What else? So we have only 4 species. Exactly. So that reaction is always there. We always have H plus and OH minus, and also H2O. So H2O, we're not interested because the whole point of doing speciation is to look at the activity, not the concentration. And we know the activity of H2O is equal always to 1. So basically, we don't need to bring that to the speciation calculation because it's already solved. So we don't consider this. What else? Hypothetically. Yep. We could have further reaction of sodium with hydroxide to form sodium hydroxide. But as you see in this lecture, it's fair to ignore it because it's a strong base. So the reverse reaction is way stronger. So we assume that that doesn't happen. So sodium hydroxide could be, but we ignore it for the whole course. What else here? Can we say sodium sulfate not dissolve sodium sulfate? So basically, not maybe all of them are dissolved, but you might get some SO4 in the solid form. We might, but it's not a part of aqueous speciation. The same thing, the activity of that solid is always also 1, so we don't consider that. But that's a very important reaction in chapter 3, basically. So that dictates the speciation in the aqueous indirectly, but it's not a part of the speciation. So now we did step 1. We have how many? 6 species. How many equations we need? So we need 6 equations. Independent equations. So if we have that, then it would be a set of equations and we know how to solve it. So eventually what this gives you is that the ability of, if you add 1 molar of sodium sulfate, you can predict what would be the pH because H plus is one of the species, and when you can calculate the concentration of that, then you can measure estimate the pH. Or opposite, if you want to increase the pH of your solution or decrease it to, let's say, 4, then you can tell how much sodium sulfate you need to add to that sample to reduce the pH. So a very useful information. So now let's look at what we have in our toolkit for equations, because eventually we need 6 equations for this example. So here we want to talk about 3 families of equations that we're dealing with all the time. Again, it doesn't matter, this is chapter 2 about acid base, but it's always there. So the first equation is from the first lecture of the course, charge balance. Very obvious. So we don't have any water that is positively charged or negatively charged. Always we have charge balance. So what it means is that sum of all the positive charges are equal to the negative charges. Or more specifically, when we talk about the amount in coulombs, then we have to, in terms of the concentration, we have to deal with both the charge and the concentration for positive species and also the negative species. So for example, 1 mole of sulfate, which is 2 minus, would have more amount of charge compared to 1 mole of chloride with 1 charge, negative 1. So that Z factor is correcting for that. So what's the charge balance for that sodium sulfate? What is on the left side? What are the positive? Yep. So H plus is easier to start with. H plus sodium. And these are always 1 times H plus 1 times sodium because Z is 1. Any other positive? Not really. What is the negative? Always start with OH minus. What else? Mm-hmm. Exactly. Yeah. 1 HSO4 minus, but 2 SO4 2 minus, because that's the Z factor. It's a delicate difference between the charge balance and also the mass balance that we're going to do later. Keep in mind the charge balance, only looking at the Z factor, the charge, also the concentration. The concentration is what we're calculating. So this is one independent equation that we have here. The origin of this equation is coming from the charge balance class of equations. And we always have one charge balance, so there's no more than one. And this would be the core equation for solving for speciation when it comes to using Excel, for example. In lecture 10, you'll see that. Always, it has to satisfy this. So the second class is basically mass balance, conservation of mass. It's something that is applied also in our system. But here, keep in mind, we're talking about closed systems. This equation, this class of equation, won't be the case in the last lecture of this chapter when it comes to gas-liquid equilibrium or when it comes to precipitation. Because when you have precipitation, you're removing something out from the system, so it's not a closed system. Or when you introduce a gas, it's basically a gas-liquid equilibrium, so you're bringing something else. But here, for this chapter, except the last lecture, it's always a closed system. So it's always what is happening in the system. So in closed system, we can use the mass balance expression for all the elements except oxygen and hydrogen. For hydrogen, it would be tricky because we're calculating pH, and the nature of that hydrogen can come from different sources, including water, hydrolysis. So it's easier to do it for the rest. So what other elements we have here except oxygen and hydrogen? Sodium, that's the easy one. Sulfur also. But for sulfur, we can just say, for the sake of simplicity, we just say this is the total of all the sulfur-containing species. Total of all the sulfur-containing species. But here, and then we have one for all the sodium. So what species contain any form of sodium among those 6 speciation? Exactly, it's just the ion itself. So the total amount of sodium in the system is equal to the concentration of sodium. How about sulfate? That's it? Exactly. So here we don't have that factor of 2 because that factor of 2 was because of the charge. But here it's basically this molecule is bringing 1 unit of sodium. This molecule is bringing also 1 unit, and this molecule is bringing 1 unit of sodium. So because of that, the prefactor is always 1. So whatever you have in the system at any point in equilibrium, the combination of all the 3 would be equal to the total amount of sodium that was added. Okay? So one tiny difference here is that, do we know this value? Exactly. Exactly. So basically, we know how much we added sodium sulfate. That's the known value. Let's say we added 1 molar. The only thing is that let's call that the total of sodium that's the known value. So for 1 mole of sodium sulfate, how many moles of sodium we're producing? 2 moles. So the total, I put it this way. So this would be equal to the 2 times, all right, remove this x, maybe it's 2 times the total of sodium sulfate we added. Now this is known, and now we're connected to this one that is unknown. And for sulfate, what would be this one? Exactly. So this would be the total. So with a little bit practice, you'll see that like it's very logical. So see that it's pretty straightforward. So now we generated 2 more equations from mass balance. So this would be equation 2. Let's call this equation 3. So 3 equations out of 6 that we needed. So the second class of equation would be the mass balance, charge balance, mass balance. The third one would be equilibrium expression, what we talked about in chapter 1. We know how species are connected together, and it's independent of mass balance, it's independent of charge balance. So basically that could gives us one extra or a few extra equations. So we know for water speciation, H plus OH minus, so we know how these two are related. So this would be our equation 4. We know the first dissociation of sulfuric acid, and this would be Ka1. And then the second one for sulfuric acid. So we got equation 4, and then this would be 5, and this would be 6. So now we have 6 independent equations. Then you can solve it, 6 unknowns. So that would be it in terms of how to do speciation. Later in the following chapters, we might revisit the mass balance, as I mentioned, for open systems. But for now, just let's consider always the 3 types of equations. Sure. Okay, that's a good point. We already have it here. So we assume, we assume that this happens. Okay, and because of that, we have the relationship between these two. Exactly, we already used that. Exactly. But in chapter 3, that would be a different story. Because in chapter 3, we have that equation of precipitation dissociation as a part of the equilibrium. But that's for an open system, so not a closed system. Yep. But for now, it's just reconsidering it for mass balance. Okay, so we start from the simplest scenario. I just want to highlight here in this example that this procedure can be applied all the time. From the simplest, that you can answer this question in less than 10 seconds, to the very complicated situation when you have a more involved system. So when I say a relatively simple, it's the time that we have strong acid or strong base. And then you roughly know how much you added in terms of the proton, then you can back calculate the pH. So anyone can tell us if we add 10 to the minus 3 of sodium chloride, what would be the pH? What's the value? You said 2? Yeah, 3. So 10 to the minus 3, based on general chemistry, we know it introduces 10 to the minus 3 of H plus. So minus log of that, it would be 3. And the answer is actually 3. But here we just want to use this as a very simple example to look at speciation, that means H plus, also the other two species that we have, just to follow the procedure we talked about for the simplest system. So we know for this example, we have the reaction of HCl. We're assuming that this is in equilibrium. H plus plus Cl minus. And then we know the Ka expression is basically relating this species in this equilibrium. So the first step is basically the species. What are the species? How many we got? 5. So H plus, OH minus all the time? 4. Yeah. So we have HCl and we have Cl minus. So basically 4 species, we need 4 equations. So the next step would be equations. So the first set of equations, as we talked about, is charge balance. Let's call this CB for the rest of the lecture, so charge balance. What's the charge balance? So what would it be? Exactly. All the charges are monovalent, so no prefactor. Prefactor is always 1. So that's the first equation. The next one is basically the mass balance. What's the element except oxygen and hydrogen? Cl, so that's the only element left. What would be the total Cl? Yep, but what is the species? Yep. Exactly. So all the species that contain Cl is Cl minus plus, or let's call that HCl and Cl minus both contain Cl. And then this would be, as I mentioned, 10 to the minus 3 molar, or equal to the total HCl. So it would be equal to total HCl. So that's the second equation. So the third class of equation was equilibrium. Or let's call this EQ. How many equilibrium we have? Yep. And one acid. Yep. So one acid-base kind of reaction. So it would be 1 kW, H plus OH minus. It's at room temperature, so this would be 10 to the minus 14. And this is 3. And the last one is Ka, Cl minus, H plus, and then HCl. And this value is 10 to the power of 3. 10 to minus pKa, or which is pKa is minus 3, so 10 to the power of 3. So this would be our force equation. So that'd be it. We have 4 unknowns and 4 equations. So the next step would be basically solving it. The easiest way to approach this is always to use charge balance equation, also for algebra kind of calculation. So to solve it, what I suggest is to look at the charge balance, which in this case is H plus OH minus plus Cl minus. And then see how you can relate all the other species to the concentration of proton. So this equation has 3 unknowns, right? And you know how this guy is related to proton, how this guy is related to proton also. So if you can convert this to somehow to a form that contains proton and some other known values, like Ka or Kw, the same thing for here, then this equation would be 1 equation and 1 unknown. How do we connect these guys to the concentration of proton? Yep. So through equation 3, basically. So through equation 3, so basically we want to relate everything to proton. So through equation 3, we know hydroxide would be Kw over H plus. How about Cl minus? Which equation we should use to rearrange? Equation 4, exactly. So if we do equation 4, then we get Cl minus equal to Ka HCl, and then H plus, just rearranging equation 4. So it seems it's not enough, equation 4, because right now we have what we did here, that was enough, that we related hydroxide concentration to a constant and only concentration of proton. But here we have concentration of Cl minus to a constant concentration of proton, but also some other variables. What's that? So what do we have? Is no, that's the concentration we added. Yep, we can do equation 2. Exactly. When we look at equation 2, this is what we have, 10 to the minus 3. And now we can calculate this concentration as a function of this guy and that guy. So you have a glass of water and you have a pipette that contains 10 to the minus 3 HCl. So that's the total. And then you add it to water, but then that's out of your control. So then HCl inside the water, after mixing, after reaching equilibrium, then it's not 10 to the minus 3. But rather, concentration of HCl and Cl minus combined together would be 10 to the minus 3, which would be a total. Yeah, exactly. That's all about the equilibrium. Yeah, that's, we have to, yeah, I had to make it clear. So this is basically the concentration at the equilibrium. Okay, so if we also take into account equation 2, eventually we get to something like this, Ka total Cl, or which would be the total HCl, divided by Ka plus H. You could also use alpha notation if you're interested to do that. And you need to do a little bit of more rearrangement to get to this one. So if we combine these two into the charge balance, then we get to this equation. H plus as it is, then OH minus would be KW over H plus. The other term would be also Ka total Cl divided by Ka plus H plus. Total HCl, yeah, it's the same. So in this case, it's the same. Yeah, to be more accurate, we have to actually have like total HCl. How many unknowns we got here? Yeah, only one unknown. What kind of equation is this? It's not linear, so what kind of equation? What's the degree of the polynomial? Minus, what's that? Second order? So we have to multiply all of them by H plus times Ka plus H plus, correct? And then we have 1H plus here, so it's a cubic kind of equation. So it's a cubic equation. So we have some tools to calculate cubic equation. Don't trust ChatGPT to do it, but like Wolfram, MATLAB, or whatever programming software you use. This would be pretty straightforward. One unknown, one nonlinear equation. But now we want to, a little bit based on the physical intuition, a little bit simplify it. And if we can simplify it to a quadratic equation, it would be easier to deal with. So this can be solved. To get the exact basic answer. But let's do a little bit of simplification. The Ka value is 10 to the power of 3, right? So let's use assumption to simplify. So can we assume Ka is way bigger than the concentration of proton? Because the concentration of this one is 1000 Ka value. The concentration of proton, 1000 mole, coming from 10 to the minus 3 HCl. So it doesn't make sense. So let's assume that. Let's assume Ka is way bigger than H plus concentration. So what happens to the equation? Let's call this star. Okay. Exactly. So in this case, we could say H plus Ka is almost equal to Ka. A simplification. It's just imagine this is 1000. This is 10 to the minus 1, so 0.1. So the combination of this would be 1000 and 0.1, which is fair to say is equal to 1000. So now we need to put this into that equation. Then what happens is basically we get H plus Kw over H plus, and then plus Ka total HCl over Ka. And now what kind of equation is this? It's quadratic. This is the second order. So this would be basically a quadratic equation. And it's easier to deal with. And when we solve it, we get to the concentration of H plus to be either minus 10 to the minus 11 or 10 to the minus 3 mole. And we know this one doesn't make sense. This one makes sense. Then minus log of H plus, which would be the pH, is equal to 3. And no surprise there. Yep. Sure. I think if we use equation 2, like this one, then you get also a Cl term here. And then if we bring Cl term here and then do a rearranging a little bit, eventually you get to this kind of expression. Yeah. I actually need to double check this one because I'm a little bit also doubting it. So every time you do an assumption, you consider an assumption, you have to check after the calculation. So here we need to check our assumption. We assume Ka is way bigger than the concentration of H plus. And when we look at the values, 10 to the power of 3 is way bigger than 10 to the minus 3. So it was a valid assumption. And now we have H plus, then the rest would be pretty simple, straightforward. You unlocked one speciation, then the rest would be up to you what kind of equation you want to use to calculate for the speciation of acid base. So now let's calculate the concentration of HCl and also Cl minus. So you can use whatever equation you want to use, equilibrium, mass balance, charge balance. My favorite is using alpha because I have the pH value and I have the K value. So I know alpha 0, which is the concentration of the most protonated over the total, is also equal to H plus over H plus plus Ka. So when I add the values, 10 to the minus 3, 10 to the minus 3 plus 10 to the 3. So it's almost 0. It's a very low, small value. Then I add this into mass balance, because I know the total HCl is HCl plus Cl minus. Then the concentration of Cl minus is equal to the total HCl, or 10 to the minus 3 mole. So from the beginning, when I asked you what's the pH, and then you mentioned this is 3, it was all because of this assumption, or this fact that the concentration of HCl is almost 0. So whatever you're adding to the system, it translates into Cl minus eventually. And that basically impacts the charge balance, so eventually gets you to a pH of 3. But we always follow the same procedure. So this was a simple case to highlight how to construct that framework of species, then equations. And here we also use an assumption of how to simplify it, because we didn't have the tool in the class to solve for a cubic reaction equation. So it seems we could have a general rule of whenever we add a strong acid or a strong base, it fully dissociates. So as you saw, eventually you added 10 to the minus 3 in that pipette to the system, but when it's introduced to the water system, the concentration of this guy would be almost 0. So that would be basically one assumption, but we could have some other logical assumptions to eventually simplify the equations. But be very careful with assumptions. Every time you're assuming something, you have to check that down the road when you do the calculation. Here we had that Ka way bigger than H plus kind of assumption, and we checked that. It was 10 to the minus 3, way smaller than 10 to the power of 3. So it's good to do that. So we can generalize this, what we observe in example 1, that whenever we use strong acid or base, it completely dissociates. So that's a very good simplification. In that case, we're sort of jumping from the equilibrium and sometimes the mass balance equation directly to the charge balance itself. The other useful assumption that later for a more complex system we see is the fact that sometimes some species, their concentration is negligible. So we can assume it is zero. For example, here it's the alpha versus pH for a biproduct acid, carbonic acid specifically. So let's say if we are at pH of 3, then the concentration, it's mostly dominated by this blue line. When we get to here, the concentration is either blue or red, but there's no green. So we can assume the concentration of green is negligible based on this region and based on the information that we have. We don't necessarily have that kind of information all the time, but I just want to highlight that sometimes you can do that. Again, make sure you're checking that assumption at the end. So in this example, in this alpha example, what it shows is that we only have 2 species of this acid present at a given pH. So might not be the most useful assumption, but this is probably too specific for this example. But the fact that you can sometimes ignore or say, oh, this acid might not be, this species might not be the concentration considerable, you can just make it negligible. But the most important one is this one, that a full dissociation of strong and acid and base. Okay, so let's do a quick example based on that assumption. 10 to the minus 3 molar of HCl, pH was 3, right? Very simple, very straightforward. What if we have 10 to the minus 12 of HCl? What would be the pH then? You know, it fully dissociates. Throw a value. It's free. 12? Yeah, exactly. That's sort of a contradiction. We're adding base, but the pH cannot go to 12. So what then? 7? That's fair. Why 7? Yeah, exactly. So the reason we actually didn't do mass balance on proton was one of the reasons with this one. So right now you're adding 10 to the minus 12 of proton, right, to the system. But then that's unlike the first example, which was the major source of proton. Right now, it's not the major source. The major source is from water electrolysis. So because of that, it's better not to do it. But regardless of that, let's do the calculation only by doing that assumption of fully dissociation of strong acid. So HCl, it fully dissociates to H plus Cl minus. Basically, fully dissociate. We know like total HCl is equal to Cl minus. So that's basically the assumption. And then the rest would be basically doing a charge balance. The charge balance is telling us H plus is equal to OH minus plus Cl minus. And we know based on water equilibrium equation of Kw which relates the two. Then it would be H plus KW over H plus the Cl minus, and then let's call this one. So you see the total fraction of HCl that we're introducing to the system. In the previous case, it was the dominant source of H plus, which was dictating the eventual H plus concentration. But here is very minor compared to what we're producing from water. So again, this would be a quadratic equation, as you see, just multiplying by both sides by H plus. Then we get to H plus 2 minus KW total HCl minus, that would be no, that shouldn't be KW. It should be H plus and then minus KW. If we solve it, then H plus we get minus 10 to the minus 7 and also 10 to the 7 minus 7. We know this doesn't make sense. This makes sense. Then pH would be 7. Any question here? So this example, or this practice, highlights the importance of doing speciation to eventually calculate pH. Because that quick calculation ends up in pH of 12, which is not the case, obviously, here. But we use that very useful assumption of HCl is fully dissociated. So that was a good starting point for talking about weak acid, which is basically the calculation is a little bit more involved. Strong acid is pretty straightforward. Weak acid is a little bit less intuitive compared to strong acid, but the basics of calculation would be the same here. As always, we do that charge balance, mass balance, and all the equations. So here we're adding a weak acid to water. We have the pKa of this propionic acid, or let's call this HPR. So this part would be the PR part, and then this would be basically the H. So that's when we talk about PR minus, that means that fraction of the molecule, that part of the molecule. And now we're adding 10 to the minus 3 of this acid, this weak acid, to the system. If it was 10 to the minus 3 HCl, the pH was 3. Now we want to see the weak acid, how much would that change the pH? Are we expecting a lower or higher pH compared to pH of 3? Higher pH. So this is a weaker acid, so it doesn't get to that final pH of 3 as like HCl. So the procedure would be the same. So first we elaborate on all the reactions that might introduce a new species. And in this case, it's basically the acid-base reaction that is producing, which is an equilibrium of PR minus plus H plus. Again, that PR minus is this part of the molecule. And this is Ka, is describing this reaction. So what are the species here? Beside H plus and OH minus? Yep, and HPR and PR minus. So if you remember HCl, the concentration was almost zero, but here we're expecting a not a zero value for HPR because it doesn't fully dissociate. Then we move on to equations. We need 4 equations because we have 4 species. Similar to the previous case, first starting with charge balance. On the left side, we get all the positive charge, which happens to be only proton, then hydroxide, and then PR minus. HPR is not charged, so it's not a part of this one. The second class is mass balance. What is the mass balance here? How many we got? Yeah, just the PR. And what's the total PR? Exactly. It's either HPR, whatever we're initially adding, all the propionic acid that we're adding initially to the system, it's at equilibrium in the system. It would be either HPR or PR minus. So this would be the second type. The third would be the equilibrium. KW is always there. H plus OH minus. Then the last one is basically Ka, which is PR minus H plus, and HPR. So as I mentioned, the easiest way to proceed with the calculation would be to always look at the charge balance and convert everything to H plus and known values. So the OH, we know how it's related, KW over H plus. Now I want to use a different kind of relationship using alpha. As I mentioned, alpha is very useful. So I want to connect the concentration of PR minus to H plus and total, which is a constant. So what kind of alpha I should use? Alpha 0 or alpha 1? Alpha 1. So basically alpha 1 is equal to PR minus divided by the total PR. And we know alpha 1 is Ka over Ka plus H plus. Doing a little bit of rearrangement, this one, and PR minus would be Ka over Ka plus H plus times the total PR. And now we can basically insert all of this into charge balance. Then we'd get H plus equal to KW over H plus Ka total PR over Ka plus H plus. As you see, it's similar to the previous case. And let's call this one, let's make it start here. So to solve this, we need to multiply by H plus times Ka plus H plus. And you know what? Let's take this to the next page. So we need to use this. And if we do that, then we eventually get to this cubic reaction. So this total PR is that total HPR, so because it's 1-to-1, so that's why we're using this total PR here. So this is a cubic equation. And when we solve it, up to you how you want to solve it, then eventually we get H plus to be 10 to the minus 3.96, or the pH of 3.96. As we're expecting, this is bigger than 3. So this is the exact answer. So now let's say we want to apply some assumption, as we did for the previous example. So let's consider the same assumption as in example 1. So what we did there was we assume that Ka is way bigger than H plus. So that was our assumption. Now we insert this into this reaction. So basically what we do is simplifying this term as we did, going from a cubic reaction to a quadratic reaction. So that would make it simplify to H plus, then Kw over H plus total PR. And when you solve this quadratic, then you get the concentration of H plus to be 10 to the minus 3, or pH of 3. It seems it's a fair number, pH of 3. How do you counter argue that if I say this is the answer? Hmm? I would say close to 3. And I did all the calculation, mass balance, charge balance. I didn't. Uh, it was all based on what we talked about. Exactly. That's the point. Exactly. So as I mentioned, you have to always check the assumption. So if we check the assumption, then 10 to the minus 4.48, which is the Ka, because pKa was 4.48, just keep in mind. Then this is not bigger, much bigger than 10 to the minus 3, the pH we just calculated. So this is not true. So we're not allowed to use the assumption. So we have to do the exact calculation, which eventually would give us the pH of 3.96. So it's because of that, as you mentioned. The other two assumptions, to just give you an idea, we're not going to solve it, but just to give you an idea. One time I assumed I'm adding acid, so proton concentration is way bigger than hydroxide concentration. So in the charge balance, I ignore the hydroxide concentration. So it's H plus is equal to PR minus. If we would do that for the previous example, it would be wrong because the concentration, even though we're adding acid, the concentration of hydroxide was much bigger. Or like it wasn't that bigger. It was 10 to the minus 7 and 10 to the minus 7. So if I do that in this case, I would still get 3.96. So that is, in this case, that's a valid assumption. The other assumption is, I would say, this is a relatively weak acid, so the concentration of HPR is bigger than PR minus. So then the total would be equal to HPR. So when you add acid, it doesn't dissociate. So if I assume that, I do the calculation, then the pH would be, again, 3.93. So very close to the actual value. And so whatever assumption you make, just make sure you go back and just check that assumption. But overall, you can, up to here, you have the equation to solve the exact answer. So that's the whole point of using algebra. Even without assumption, you really don't need assumptions just for the sake of simplicity. And sometimes to have a quicker, faster approximation of your system. So to wrap up what we talked about, I think it was pretty straightforward in terms of the logic we pursue. We talked about N species. We practice how to define what species, what potential species we have based on the reactions, based on the acid base that we might have in the system. Then we had N equations. And then we basically solved. We use algebra, sometimes in combination with assumption. As I mentioned, this would be the foundation for the rest of the lecture, for the rest of the course, actually. Right now, we had 4 species. At the end of this course, we get to a scenario that we have more than 20 species. So it's basically more and more involved. But the foundation would be always the same. And in the next lecture, we're going to talk about graphs and how to use them to solve for speciation eventually.